Okay, our next speaker is Mikhail Vasilyev, TASEP and Integrable many-body system. Please, Mikhail, start.
Yeah, thank you. It is a great honor for me to give a talk on this conference dedicated to the birthdays of Leonid Olegovich and Nikita Andreevich. I can say that almost everything I know about quantum integrable systems, algebraic Bethe-ansatz, I know because of Nikita Andreevich. He taught me a lot. He gave a great course on algebraic Bethe-ansatz. And also, I would like to say that Leonid Olegovich also helped us during our studies of matrix models due to his great lectures given at Sokolov Mathematical Institute. So I would like to start my talk, and it is entitled TASEP and Integrable Many-Body Systems. So it is based on our joint work with Alexander Gorsky and Andrei Zotov. So the subject will be about quantum integrable systems and their connection with classical many-body systems, also integrable. So my plan is firstly to review several types of dualities in integrable systems, well known. Then I will give an example, quite a new example of what we call quantum classical duality between TASEP model and what we call Goldfish models, which are certain limits of Ruijsenaars integrable many-body system. Then I will talk a bit about generalizations of all of these dualities and maybe discuss some results if there will be time. So first of all, I would like to talk about several different dualities in the world of integrable systems. So the first one is what is called PQ duality, Ruijsenaars duality, action angle duality. These are all the names for one particular duality in the world of classical many-body integrable models like Kalodger-Moser model, Ruijsenaars model, Toda system. Then there is a spectral duality, which is about quantum and classical spin chain models. And then I will consider quantum classical duality, which relates now two different types of systems. The first one being classical many-body integrable system, and the second one, quantum spin chain or quantum Godin model. So on this slide, I will talk about the simplest case of PQ duality. So there is some quite long calculation, but very simple. So the idea is quite simple. So using Hamiltonian reduction on the cotangent bundle to group GLN, we're choosing an appropriate moment map. So we have two matrices P and Q. We have a symplectic form, and we can consider a Hamiltonian trace of P squared. So we introduce a symplectic action of group GLN. And then we can find out that on the reduced space, this Hamiltonian H, which is a trace of P squared, becomes a second Hamiltonian of Kalodger-Moser system. However, we could have chosen the different Hamiltonian. So P and Q, they do not differ really in this case. So we could have considered Q squared, for example, and then choosing the same moment map and the same level of moment map, we will find out that the Hamiltonian on the reduced space will be again a Kalodger-Moser model, but with a bit different coupling constant. Here is some words about that. So the only thing that will change is that coupling parameter nu will become minus nu. So this is not really seen on the level of second Hamiltonian, but it will be seen at the level of first Hamiltonian, of other Hamiltonians. So, and this is the simplest example of what is called PQ duality. And the interesting thing about this duality is that we have two integrable many-body systems. And there is a map between them that interchanges coordinates and action variables. So it is very easy to see that if we consider Hamiltonian as trace of p squared, then integrals of motion will be eigenvalues of p, and coordinates will be eigenvalues of q. And if we consider the second example, when Hamiltonian is q squared, then they are interchanged. So here is a table of dualities. So rational Collier-Moser systems are self-dual in the sense that there is a small change in coupling constant. And there is an interesting thing that trigonometric Collier-Moser is dual to rational Ruijsenaars model. So in Collier model, we have a rational dependence on moment and trigonometric in coordinates. And in rational Ruijsenaars model, we have trigonometric dependence on momenta and rational in coordinates. And trigonometric Ruijsenaars-Schneider model is again self-dual, again with some change in coupling constants. So this is the first duality. So now I would like to say a few words about spectral duality. So spectral duality is about spin chains or Godin models, which are certain limits of spin chains. So here is the simplest example, but the main idea is that we can consider two different Godin models with different, so in Godin model, you have a Renkov system. This is the size of these matrices, spin matrices, and the number of nodes, so the number of spins. So n big here is the number of nodes, and n small is the size of these matrices. So then one can consider another Godin model, but here something is interchanged. So in the first model, ZQ were what we call inhomogeneity parameters, and lambda, which is a diagonal matrix, is a twist matrix with diagonal elements lambda 1 and lambda n. So in the dual model, the inhomogeneity parameters and twist parameters are interchanged, and the duality can be stated as simple as possible. So roughly speaking, the spectral curves in this sense are almost identical. So this is the first type of duality, which is called, which interchanges inhomogeneity parameters in spin chains and twist parameters, and also changes rank with the number of nodes. So here is a table of spectral dualities. Rational Godin model is self-dual. XXX spin chain is dual to trigonometric Godin model. XXZ spin chain is dual to XXZ spin chain. It is self-dual. Also, there is a quantum version of this duality. And also, this is very interesting, connected with what is called dynamical KZ and dynamical QKZ equations by Tarasov, Varchenko, and many others. So, and the third duality, which we'll be working with, is what we call quantum classical duality. It connects the systems from the world of classical integrable many-body systems. Here is the simplest example. We take a rational Kalodger-Moser model with such a potential, and it is well known that this system is integrable. It has Lax representations with the following L matrix. And this is actually everything we need to know about this model. So, and we consider Godin model. So with inhomogeneity parameters ZE and twists. So in the Godin model, we try to find eigenvalues of the following operators. So here V is a twist matrix and Pij are permutation matrices acting on the tensor product of the space Cn. So, and the answer is given by Beth ansatz. So the eigenvalues have the following form, where we have some unknown parameters mu, which are called Beth roots, and to find Beth roots, we have to solve this system of equations. So we reduced a spectral problem for these operators to solving some algebraic equations. So what is the duality I'm talking about? So the statement of the duality is the following. So here's the table. So in Kalodger-Moser system, we have a coupling constant, mu, we have coordinates, and we have velocities q dot, which are actually equal to momenta, but in these dualities, it is better to talk about velocities. And the integrals of motion are eigenvalues of Lax matrix. In the Godin model, we have Planck constant h bar, we have inhomogeneity parameter z, we have Hamiltonians of Godin model and their eigenvalues, and we have twist parameters. And I claim that if we set mu equal to h bar, if we identify coordinates and inhomogeneity parameters, and if we identify velocities and eigenvalues of non-local Godin Hamiltonians, then eigenvalues of Lax matrix, which are first integrals of motion for the Kalodger-Moser system, have very simple form. So they are represented as only twist parameters. So these are twist parameters with some multiplicities, which depend on the number of Beth roots. So in the previous example, I had a very simple model, which could be called GL2 model. But if the rank is bigger, then there is a tower of Bethe equations. There are several number of Beth roots, several types of Beth roots on different level. So M1 and Mi are the number of Beth roots on a certain level, and the integrals of motion of classical Kalodger-Moser system are given by twist parameters of Godin model with some multiplicities. So this is the statement of the duality. And now I would like to give a table of these dualities. So here we have, first of all, rational Kalodger-Moser model, which is dual to rational Godin model. In the same sense, trigonometric Kalodger model is dual to trigonometric Godin model. Rational Ruijsenaars is equal to XXC spin chain, and trigonometric Ruijsenaars is dual to XXZ spin chain. And also we know some other classical integrable many-body systems from Toda family, which could be viewed as a limit from Ruijsenaars family via what is called an Zemtsov limit. So, and we actually can ask ourselves what will be dual to the Toda family on the spin chain side, and actually there is some answer, not given in the way that we're used to in quantum integrable systems, but with quantum cohomology approach by Giventhal and Kim. So there is another approach using Hecke algebras, but I will talk about this a bit later. So now I would like to consider a small diagram which represents how all these dualities are connected with each other. So we can consider, first of all, trigonometric Collider model with coordinates q and action variables I. So I can do PQ duality, and I will obtain rational Ruijsenaars model with coordinates and action variables interchanged. And also I can do a quantum classical duality. And to Collider model, I will obtain trigonometric Godin model, and coordinates will become inhomogeneity parameters, and action variables will become twists. And here I have spectral duality with x-axis spin chain, and again, twist parameters and inhomogeneity parameters are interchanged. And again, here I have a quantum classical duality. And again, action variables are still twist parameters, and inhomogeneity parameters are still coordinates. So this is the idea how these dualities are connected with each other, which is, I think, very interesting. So here I would like to talk about a certain limit of Ruijsenaars-Schneider model. So of course, we all know that there is a limit from Ruijsenaars-Schneider model, which is sometimes called relativistic Collider system. So if we consider eta as an inverse speed of light, then the limit eta to 0 is a non-relativistic limit, and in this limit, Ruijsenaars model becomes a Collider model, a rational Collider model. But actually, we have two parameters in the Ruijsenaars model, eta and c. So the limit to Collider model is eta to 0, but we want to consider a limit. The parameter c goes to infinity. And here we perform such a limit and obtain the following Hamiltonian. So we call this model a Goldfish model. They were obtained by Collider and Ruijsenaars in different time. So what is interesting about this limit is that this limit is quite interesting, I would say, because we know that Ruijsenaars-Schneider model is integrable. It has a good Lax representation. We can find first integrals using the Lax matrix, but in such a limit, the Lax matrix becomes of rank 1, thus not providing enough integrals of motion for the integrability. So this limit is quite peculiar. It do not interact in a good way with the Lax representation. So what can we do to preserve integrability? And the answer is very simple. So Ruijsenaars, in his paper, I do not remember the year, but a long time ago proved that these models are integrable. So in the rational case and in the trigonometric case, we can write down all the Hamiltonians explicitly. Although there is no known Lux representation, we just know the Hamiltonians explicitly. So, and here I write them using velocities and coordinates, and about velocities one should think in the following form, as the following function of momented coordinates, and in the trigonometric case, almost the same formula is true. So here are some coefficients which are not important for the classical integrability, but we just write them for the convenience. So Ruijsenaars proved that all these integrals are independent, enough number of integrals are independent, and they all Poisson commute. Thus, this is an integrable system. Okay, so another thing that I would like to point out that this limit, c to infinity, in which we obtain these Goldfish models, could be viewed as something connected to Inozemtsev limit, which I talked about earlier. So using Inozemtsev limits, we can obtain Toda family from Kalodger and the Ruijsenaars systems. And actually, there is a theorem. So Ruijsenaars found all these models during his studies of PQ duality, or what we call now Ruijsenaars duality, which I talked about earlier again. So he found them in a search of systems PQ dual to Toda systems. And there is a theorem that says that rational Goldfish model is PQ dual to non-relativistic open Toda chain, and trigonometric Goldfish model is PQ dual to relativistic open Toda chain. So, and again, there is an interesting question, how to describe in the quantum integrable systems fashion the system which will be quantum classically dual to Goldfish models and Toda models. And so the answer for the Goldfish models is the following. So if you remember that Ruijsenaars-Schneider models were quantum classically dual to spin chains, XXC spin chain and XXZ spin chain, and we have done some limiting procedure in the Ruijsenaars models. So we have to do a certain limiting procedure in XXC and XXZ spin chain. So I claim that this is possible. This is quite not an easy exercise to find a correct limiting procedure, but one can find the following quantum R matrices. So the first one is in rational case. So here is the simplest example in the 4x4 case. And here is the simplest example for 4x4 case in the trigonometric case. And so why my talk was entitled TASEP and Integrable Many-Body Systems. So Integrable Many-Body Systems is, of course, about Goldfish models. And TASEP actually comes here in the following manner. So if we consider this R matrix, so this is an R matrix for a celebrated multispecies TASEP model. So just to give you a feeling what quantum integrable systems we will obtain using such R matrices. So here is simple example. So if we consider the simplest case when all the spaces, all the quantum spaces are two-dimensional, in the rational case, we will consider by quite a simple procedure. using our matrices, we can construct monodromy matrices, then we can construct transfer matrices, and we can construct a local Hamiltonian for a quantum spin chain. So in the rational case, we will obtain the following following Hamiltonian, which is just written using sigma matrices. So this is in the rational case, and in the trigonometric case, we will obtain the following Hamiltonian, which actually, why it is called TASEP, totally asymmetric simple exclusion process, that if we consider not eigenproblem for this Hamiltonian, but if we consider the evolution induced by this Hamiltonian, it will describe a system of particles and holes on a ring in our case, moving, I guess, to the right in time with some probability, and only on the right. This is why this is called TASEP totally. So this means that particles are only moving to the right or to the left. This depends on the form of the Hamiltonian. So so here is a slide briefly describing how we construct quantum integrable spin chains using quantum R matrices. So here, as I earlier told, here is a monodromy matrix. It is just a product of twist matrix and R matrices with homogeneity parameters. And construct transfer matrix, which commutes with itself in different points, thus providing commuting integrals of motion. And all our R matrices have a very simple pole structure, so we can use residues in inhomogeneities to construct our commuting Hamiltonians. So, and again, we want to find eigenvalues of such Hamiltonians, and the answer is given by nested Bethe ansatz in the similar manner as it works for XXZ spin chain or XXC spin chain. There are no problems with that. So, and here is eigenvalues and Bethe equation. In the rational case, and here in the trigonometric case. So here we see that U are Bethe parameters. They have two indices. The first one counts the number of Bethe roots on a certain level, and the upper index is about a level of nesting. So to find an eigenvalues of these Hamiltonians, we have to solve a very complicated system of equations. And so the statement of the duality is the same as earlier. We identify in the rational case coordinates and inhomogeneities, velocities and eigenvalues of the Hamiltonians, and then we find that the level of classical Hamiltonians are exactly the twist parameters, and they're written in this not very simple form, but this is just the artifact of the fact that we have done some peculiar limit. So what is quite non-trivial about all of this, that if we just substitute in the classical Hamiltonians for the velocities, we take eigenvalues of quantum Hamiltonians, eigenvalues of quantum Hamiltonians are written with the help of Beth roots, which are not known. So there is a quite tricky method quite technical, but very tricky to rewrite these classical Hamiltonians in the following manner, that we can use Beth equations in them to simplify them and to get rid of all the Beth roots except for the last ones, and just to prove this statement. So I'm quite short on time, but I'm almost done. So the same holds for the trigonometric case. And for the trigonometric case, we have a duality between TASEP model and trigonometric Goldfish model. So here is the expression for the classical Hamiltonians is again quite non-simple, which is connected to the limit that we have done. So, and actually, why all of this is non-trivial, everything for XXE and XXE spin chain was known, and for Ruijsenaars models dual to them. This case is non-trivial because, again, as I told, for the Ruijsenaars model, we have Lex matrices, and we can work with them. We can try to diagonalize them, find the eigenvalues. But in this case, we do not have Lax representation, and we have to work explicitly with Hamiltonians. So we can quantize such a duality in the following sense, that we can consider not quantum spin chains, but QKZ equations connected to them. So, and the relation between and on the many-body side, the classical system is just quantized. So here are the shift operators, and these are quantum Hamiltonians for many-body systems. And in this, and here the statement of the duality is the following: that using the solutions of KZ equations, we can write solutions for the many-body problems, just taking a scalar product with some covector. So here lambda k's are eigenvalues of obtained functions. So they are the same as in the quantum classical duality mentioned before. And here is again a table of dualities, just to illustrate that everything here is connected. So we have trigonometric Ruijsenaars model, which is PQ self-dual. We have limit to rational Ruijsenaars. We have limit to trigonometric Calogera. And here we have from rational Ruijsenaars, we have a limit to rational Goldfish. Here we have limit to inozemtsev limit to open to the chain. Again, here we have PQ duality. Here we have quantum classical duality with what we call 5 vertex models and models mentioned before with R matrices that were written before. We call them 5 vertex models just because in the simplest case, 4x4, they have 5 non-zero elements. And actually, one of the interesting questions is to describe in a quantum integrable systems fashion the systems that will be spectrally dual to 5 vertex models. And again, they can be, in some sense, they can be written using degenerate affine Nilhecke algebras. So, but I think I'm quite short on time, so I will just skip all of that. Here is a version of quantum duality for the open to the chain. But I think that I should end here, and I would again like to congratulate Nikita Andreevich and Leonid Olegovich. And again, thank you. for your attention. I hope that this was interesting for someone. Thank you.
Okay, thank you very much. So please, questions, remarks?
And could you show page 17?
Why do you always ask about page 7?
Not 7, 17 this time.
7.
Okay, yeah, the bottom. Oh, yes.
Yeah.
So the result for this Hamiltonian, how it was obtained, could you say a few words?
Okay, I will try to do this short. So if you ask me why the answer is so not good looking, then
It looks perfectly in my opinion. And it reminds me very much a result for some determinant considered in the work by, I think, Gorsky, and Zotov, some determinant for involving roots of beta equations.
It is almost the same, but
so did you use this or not?
No, we cannot use this here because we don't have a lax representation. So we have to work really explicitly with all of these Hamiltonians, but we have to use some trick to rewrite rewrite classical Hamiltonians in such a form that beta roots and coordinates will be interchanged. And then in this form, we can use beta equations to get rid of coordinates. And then we will have an expression very similar to classical Hamiltonians, but with the first beta roots and the second. Then we again use our trick to interchange them.
You exclude, yes, step by step.
Yeah, I exclude all the beta roots. And then I come to the situation when I have only the last beta roots, and then I just do an explicit computation.
Okay, so it looks very similar to what I was saying about this. So this actually this Hamiltonian, so it can be written as a determinant of some matrix with beta roots.
I think yes, but I'm not sure now that really determinant. But as some data of some matrix, I think yes.
Okay, so we will have some time to discuss it later. Okay, thank you.
So if no questions, we may stop here and we have a break for